Okay, now so let's look at the top section and the bottom section. So for the top section, I'm gonna go for the top section first, and then we will see the bottom section, the stages for the top and bottom section. So I'm removing the comments here, and now let's go quickly to see what we were doing here. So first, if you remember, this is the equation that I used to calculate, which is the equilibrium relation. I calculated y as a function of x before, and this was x as a function of y. And actually, this was simple to do. I'm just gonna run the file based on the first equation using this code, and this is what we did. Let's go for the R minimum 1.5 for instance of our memory. Okay, so this is exactly what I'm talking about. Let's focus the axis on this part. So what we did is that we got this this horizontal line which had the same y here and here, and we knew the x here and the y here, but we here know only we only know the x here, and that's why we needed to get the equation, the equilibrium relation, x as a function of y, so that we know the value of y, but we don't know the value of x. So we need to get the value of x, which is this value of x, based on the value of y. Okay, so this is why we needed to put the equation, the x equilibrium that I put here. Okay, so this was very simple. It was a kind of piece of cake when we were using the first equilibrium relation, because it was a simple relation. You can get x as a function of y, and with some simple mathematical manipulations, you can get y as a function of x. However, for the second equation, for the equilibrium relation that is complicated this way, you cannot do it. You have already 3 parts, so you cannot break it into 3 parts and do each one separately. The second thing is that the equation is, even each one of them is in the x to the power, or to the power 3 and power 2 and power 1, so it's kind of, I think it's impossible. There's no way I know that can get y as a x as a function of y. So we need to find a way actually to do this. And if you think about it, what we need to do is to get the value of x, I mean the value of the value of x that will make the y here at this point equals to the y here. So this is the target. We did it before by putting x as a function of y, so we put the value of y and calculated x. You can do it by iterations, so this is what we're gonna do now. So if you go through the steps that we were using to calculate the top section stages, this is the x equilibrium, which is y as a function of x, I mean x as a function of y. And we put the top section 1 and 2, and we already went through it. So this is y top 2 equals y top 1. When I say this y equals this y, the problem will come here when I calculate x, and this is what we did here. We said x top 2 equals x equilibrium of y top 2, and here comes the problem. This equation has nothing wrong with it. This equation is calculated from the top section equation, which has nothing to do with the equilibrium relation. So the rest of the loop has no problem. We only have the problem here. So what we're gonna do is to do some simple if solve relation. So I'm gonna use the if solve, and what I need to do is to get the value of y that will make the I mean the value, I'm sorry, the value of x that will make the equilibrium relation equals to y top 2. So I'm gonna make a function handle of x, and the equation that I want to solve is the y equilibrium of x. Okay, this is already the name of the equation. I just want to make sure that this is the name. Yeah, it's y equilibrium of x minus the y top 2, and that's it. So what I'm doing here is that I'm asking it to get this equation equal to 0 by changing the value of x in the y equilibrium relation. Okay, and I'm gonna put some initial value that is I'm gonna make the y top 2 for instance, or the, let's make it x top 1. So you use x for x, and then I put the options so that we don't see all the iteration results. So now we should be good to go for the rest of the code. It should be good. So let's try it. And this is what we did. So even when I'm using the ideal case, it's working. And this is the beautiful thing about what I'm doing, is that it's not gonna matter if you're using an ideal equation or the non-ideal equation. So now if I move from equation 1 to equation 2, and run the file, it's gonna work, and it's awesome actually. And this is very good thing to see with your eyes, and it tells you a lot of concepts. When you see the results here, I didn't show the number of stages. So this was for the top section and the actual stages for the top section. So I'm now running the file. You see that we are using 21.14 actual theoretical stages and 61 actual stages. So 21.14, let's look at the plot. You have here one, this is the fraction actually, this is the 0.14, this is the 0.14, and then 1, 2, 3, 4. So I have now almost 4 stages to reach 0.9, and this is the 4.17, and I have 17 stages just in this part. And this is because I'm gonna focus again at this part, and you see that this operating line and equilibrium curve are very close to each other, and that's why the separation is extremely difficult, and that's why you need to have more and more stages just to reach the 99.5% accuracy, or I'm sorry, purity that you are trying to get. And that's why you're using a very high value of R minimum here. The R minimum here is 1.5, and the R is 2.3. Before it was 1.0 something. So it is giving you some physical meaning of the numbers that you're using. For the bottom section, it's not gonna have any issues actually. We should be good to go with the current code, and this is because I didn't need to get x equilibrium as a function of y. We went the other way. So for the bottom section, we started here, and we know the x and used x to calculate y, which is the original form of the equilibrium relation. So I have no problem with the y equilibrium. And this x bottom is the operating line of the bottom section, which is a linear relation that has nothing to do with the equilibrium curve. So I'm good now. So now we can work with the code now, the full code, to calculate the number of stages for the bottom and the top sections. And if we run the file now, you'd see that the stages are calculated right. You'd see for the bottom section, although we are going from or starting with 60%, which is the feed composition, we are using only 1.83% stages. So it didn't even reach 2. It's 1.83 stages, and this is because the equilibrium curve here is way further from the bottom section line than the top section, or than it is from the top section. So it's important to know that, or to understand that concept, that as the operating line gets farther from the equilibrium curve, you have a very big driving force. You don't need to put any much effort to get the separation done. In the other case, if the equilibrium curve is close to the top section, you have very weak driving force. You have to give it more and more time and space, and give it the opportunity to do the separation as much as it can. So you have many stages here. The total number of stages, the actual number of stages here are 67, 61 plus 6. This 67, more than 90% of the stages are just in the top section, and I would say like 80% or maybe more is just in this part of the diagram. So it's very good to to try to grasp the concept and to understand how this reflects the mass transfer concepts that we need to keep in mind while working with such systems. So now the code is good. You can put any other equilibrium relation here instead of this, and it's gonna be working very, very nicely. Everything will work just by referring to the equation that you need to use. And now we know from the previous videos how you can get the equation that fits well with your data to get the accurate fitting. So it's just about the fitting, and everything would be as it is. You don't need to worry about anything about the Q line. You don't need to worry about the R minimum. You don't need to worry about anything. So I hope it's useful, and I hope you like it, and I'll see you in the next video, inshallah. Goodbye.